como sempre, o seminário vai ser gravado no IFGW, vai ser no canal IFGW, então se você fala, todo mundo lembra que vai ter muito. Hoje temos a honra e o prazer, mais ou menos um pouco antes do 10º aniversário da descoberta das ondas gravitacionais, não sei se eu já estava aqui. Nós temos um dos especialistas das ondas gravitacionais, é membro do LIGO. Alexandre é francês. Agora eu fiz doutorado no Instituto de Astrofísica de Paris, e depois fiz postdoc na Universidade de Maryland, e agora ele está no observatório, mas ele é teórico, mas as ondas gravitacionais, ele acabou de me explicar, teóricos experimentais interagem muito mais que outros grupos. Ele está para um ano visitando o grupo dedicado ao Astronomia no Instituto Teórico de São Paulo. Vai dar para nós Please, por favor.
Obrigado. Eu espero que eu preciso não fazer o seminário em português, porque vai ser bem difícil para mim. Tá tudo bem fazer em inglês?
Idioma do seminário entre português e inglês aqui na escola do mestrado.
Perfeito. Então, I'm going to switch to English. Thank you for coming. And before I even start, I would like to say, if at any point you have questions, since there's just a few of us, please don't hesitate, stop me, raise your hand, and let me know if I'm not clear or whatever, and you have a question. I'll be happy to try to clarify. So, as Giorgio said, we are celebrating the 10th anniversary of the first direct detection of a gravitational wave. It was emitted by a binary system of black holes, each one having more or less 30 times the mass of our sun. That was, I think, the 14th of September, 2015. And so we recorded this gravitational wave sourced by the orbital motion of those two black holes using instruments that I will be talking about a little bit, called LIGO and also Virgo. And what I want to do is kind of give you a broad overview of gravitational wave science during this seminar. So I'll start by reminding you what is a gravitational wave, what are their properties, how do they differ from electromagnetic waves, and then I'll discuss the kind of science that we've been able to do over the last decade using many detections and more detections of gravitational waves using very sensitive instruments. And if I have time, I'll also touch upon some of the work I do, which, as Giorgio mentioned, is of a theoretical nature that has to do with trying to predict very accurately the shape that those gravitational waves have to be able to detect them. As I'll show, in fact, the signal is typically buried inside the noise, and so to detect the signal, you need to have an idea, a very precise idea of what the shape of the signal is. And then you do so-called cross-correlation between your data and the template, the theoretical prediction, to extract the signal from the data, if it's there. So there is this theoretical work that has to be done, which is a large part of my research activity. So let's start with gravitational waves. So in one sentence, a gravitational wave is basically a tiny perturbation in the curvature of space-time that propagates at the vacuum speed of light. So I like to illustrate this with this diagram where you imagine you have a sort of average background curvature of your background metric here. So if there's no source of gravity, your background metric could be the Minkowski metric, then the associated curvature would be 0. And on top of that, you have this little ripple that's propagating. Usually we note it H. The full metric would be the sum of the background and the perturbation, and it's propagating on that background at the speed of light c. If it's a wave, so it obeys a wave equation, which I'm writing here, right? It's a D'Alembert operator acting on the metric perturbation. You can have a coupling between the perturbation and the background curvature. And just like in electromagnetism, you have some source. Here, the source is not a current, it's the energy momentum tensor. This is coming from linearizing the Einstein equation around this background metric G. And this is a key prediction of Einstein's general theory of relativity, along with the existence of black holes and the dynamical nature of the universe. So it was predicted in 1916, and they were detected in 2015, almost like 100 years later, for the first time. So if you like space-time diagrams, so you would have like space in that dimension, time in that dimension. You and I, at zeros over the approximation are just world lines in space-time. And the path of a light ray would be like this, traveling at the speed of light. So material bodies are always inside the light cone at every event in space-time. And a gravitational wave would then be some sort of ripple here in this sheet of space-time to visualize what is gravitational wave. And it, as you can see, it propagates at the same speed as electromagnetic waves. So it's nice to always try to contrast the properties of electromagnetic waves and gravitational waves to get some more precise idea. So the origin of electromagnetic waves is, of course, oscillations in the electromagnetic field, while in the case of gravitational wave, it has to do with space-time curvature, as I said. The source of electromagnetic waves are the accelerated charges, while by analogy would be the acceleration of mass, or more precisely mass energy for gravitational waves. The wavelength is typically much less than the size of the source. That's a big difference between electromagnetic waves and gravitational wave, where typically the size is much larger than the size of the source, so you can't make an image of a source of gravitational wave typically from the wave itself, contrary to electromagnetism. That's related to the regime I'm going to talk about, where the typical separation is much larger than the size of the source. The typical velocity is much less than the speed of light. And then you can show that the typical wavelength emitted, which is related to the frequency of the wave, right, is related to the orbital motion. And then when you do this order of magnitude estimate, you'll find it's much larger than the typical size of the source in the post-Newtonian regime. It becomes of the order of the size of the source. So at the end, the typical frequency of the wave emitted by the final perturbed black hole.
You can shake with a very small amplitude, but if you're going to orbit, it's probably a big amplitude.
If you're going to
dipole versus quadrupole. Dipole is shaking, quadrupole is orbiting, something like that.
Well, I guess you could also put two charged particle in orbit, not necessarily just shake them. The dipolar versus quadrupolar has to do with conservation of charge in electromagnetism and conservation of mass and conservation of linear momentum in the case of gravity.
But it also affects the wavelengths. Dipole motion is shaking.
Yeah.
Quadrupole motion is more complicated.
I see what you mean. Oh, okay.
I mean, sure, in principle, you can do orbiting charges, but most charges
sure.
Charges.
Yeah, if you do that with a gravitational source, you will not generate gravitational waves. Yeah, indeed. So indeed, the structure is dipolar for electromagnetic waves, quadrupolar for gravitational waves, and that has to do with conservation laws in physics. So that's a big difference. The coherence is typically high for gravitational waves and low for electromagnetic waves. What I mean by interaction here is that the electromagnetic interaction is much stronger than the gravitational interaction. So in a sense, it's very nice for gravity because it means once the wave has been generated by the source, it's going to interact very weakly with all the matter that's in the universe between the source and you. So it means you get it almost unaffected. So it's a very good information about the source itself. Of course, on the other side, it also means it's going to be very hard to detect it, right? If it interacts poorly with everything, it also interacts poorly with your detector. So it's going to be tricky to detect the gravitational wave. The typical frequency of the electromagnetic waves we're interested in are so high that we generally don't track the evolution of the amplitude of the field itself, because the electronics would not follow. Typically, we are more interested in the power, right? The average electromagnetic strength squared. While in the case of gravitational wave, the typical frequency is low enough that we can actually track the time evolution of the amplitude of the field, and that means that this is decaying like the inverse of the distance to the source. So you have access to potentially very, very distant sources. And if you want an analogy, one could say that with electromagnetic waves, we are seeing the universe, and we are sort of listening to the universe with gravitational waves. Of course, gravitational waves are not sound waves, but I'm just trying to say, it's a complementary way to get information about the universe. Very, very different from electromagnetic waves. Just like there is an electromagnetic spectrum, there is a gravitational wave spectrum that ranges from 10 to the minus 16 hertz to a few kilohertz. And that corresponds to typical wave periods that have to do with here the age of the universe, like say 13 billion years or so, or 14, to eventually milliseconds, or even less. Depending on the frequency range of the source of the gravitational waves, you're going to have different detectors. We are mostly interested in this talk in terrestrial interferometers, which are already taking data, whose sensitivity is roughly between 10 hertz and a few kilohertz. There is a project to send in space a gravitational wave detector called LISA in 10 years from now, which will be sensitive to much lower frequency, between a fraction of a millihertz and 1 hertz, more or less. You can also use so-called pulsar timing array at lower frequencies, and also look at the imprint of some gravitational wave or cosmological origin on the cosmic microwave background data at even lower frequencies. And these correspond to very different sources, okay? Because depending on the mass, typical mass of the source, it's going to emit at different frequencies.
This last one is B mode, right?
Yes, exactly. B mode. No, there was a collaboration that claimed to have seen it, but actually it was interstellar dust. Yeah. It was a false detection. So there are especially promising sources of gravitational waves. Well, some of them are not just promising. They are, as we'll see, have been detected using LIGO and Virgo. So with this frequency range, we are already seeing the coalescence of binary system of more or less stellar mass compact objects. So by compact object, I mean a neutron star, whose mass is of the order of 1.5 solar masses or so, and black holes, whose mass we'll see can range from a few solar masses to apparently even hundreds of solar masses, which was kind of a surprise. So we're already seeing those systems, and also the coalescence of a neutron star with a black hole. We're still hoping to see a signal from a core collapse supernova that may happen anytime in our galaxy. That's supposed to happen statistically more or less once every century. Hopefully, it could be tomorrow. Hopefully, we won't have to wait another 200 years. And in the future, LISA will see sources which are much more massive and therefore emit a much lower frequency, such as the coalescence of two supermassive black holes. You may have heard that every galaxy analogous to ours, the Milky Way galaxy, harbors at its center a supermassive black hole whose mass can range from a few million solar masses to a few billion solar masses. And during the cosmic evolution, those galaxies end up merging, and the supermassive black holes in them, we think, also end up merging. So that generates gravitational waves that LISA will be able to see, as well as other sources I'll mention later on. So I already mentioned this idea. It's not enough to have great detectors. You also need to know what to look for, because basically the typical amplitude of your signal is buried into the noise. Here I'm showing a diagram with half a second of simulated noise in one of the LIGO detectors in light blue. And buried in there, you have a signal in red, h of t. If you don't know what it looks like, you will never see it, right? Let me just amplify by a factor of 100. That would be the typical shape of the signal you expect from a binary neutron star. So the frequency and the amplitude of the signal is increasing with time, just because the binary neutron star is losing energy to gravitational waves. So the orbital frequency is increasing, and that means the gravitational wave frequency, which is proportional to the orbital frequency, is increasing, and also the field is becoming stronger, and so the amplitude of the waves emitted is becoming stronger. So as a function of time, you see this increase in frequency and amplitude. In Fourier space, that will look like that. So the key point is that if you know the shape of the signal in advance, you can filter the noise and recover the signal using so-called matched filtering. Hence the need for theorists like me we need to predict very accurately the shape of a wave generated by a given source. So basically, I start with the Einstein equation. I give myself two compact objects with mass m1, m2. Eventually, they can have spin. They may precess. You can add lots of physics. And then you try to see what's the orbital motion and what's the associated wave generated. So you need to solve that problem to give it to your colleagues who are doing data analysis, who are using very sensitive instruments to detect those gravitational waves. So here's an example, one of the first signals detected, the 26th of December, 2015. Oops. We've lost the image. It's back. As seen in the data of the two LIGO detectors in Hanford and Livingston. So here's the noise in blue and red. And here's the signal which is buried in there. Here's the accumulated signal-to-noise ratio as you're doing this match filtering technique. And once you're above a certain threshold, you might claim that you have detection. OK, so how are we doing this gravitational wave science using those ground-based interferometric detectors, which are basically kilometer-scale Michelson interferometers, where the length of the arms here is of the order of 3 or 4 kilometers here and here. There are two detectors in the US called LIGO, one in Europe, in Cascina, close to Pisa, called Virgo, which is an essentially French-Italian collaboration. And there's also a cryogenic detector with more advanced technology, which is a bit more experimental, which is called Kagra, which is in the Kamioke mountain in Japan. And they are all active. And there's a plan to move one of the LIGO detectors also in India to have better accuracy in the sky localization. Because you want to put your detectors in very different planes, basically, at the surface of the Earth. So here's the roadmap for the ground-based detectors for LIGO, Virgo, and Kagra. A very recent figure. You see that there have been already 4 so-called observing runs that we call O1, O2, O3, O4. So the first one started around 2016, 2015, 2016. There were 3 detections at the time. Then there was O2, O3, and right now we are finishing O4, see, right before the end of 2026. I think O4 is supposed to finish in 2 weeks from now. And then there should be another upgrade, because every time you stop, you basically upgrade your detector. You make it more sensitive so that you can see sources further away, so that you increase the event rate, the number of detections per year, say. And that's translated here in some typical distance up to which you can see a canonical bi-neutron star system. So 10 years ago, we could see up to 80 megaparsecs. Right now, it's like twice as much. If you can see twice as far, you can see a volume 8 times larger. So that means you're going to see roughly 8 times as many sources per year, per unit time, in fact. OK? And hopefully, in 5 years or so, we'll have O5 with even higher sensitivity and higher even rates. So you can also look at then the number of detections as a function of time for each observing run. As I said, first observing run, 3 detections. And then second and third, we went from a few events to a few tens of events. With O4, we have a few hundreds of events. And with O5, maybe a few thousands. And with next generation detectors like the Einstein telescope or Cosmic Explorer, we'll be talking about maybe hundreds of thousands or millions of events per year. So that's what has actually been performed so far. The cumulative number of detections as a function of this effective time volume. So the longer you observe and the larger the volume you observe, the larger the number of events. And you see indeed that you go from a few to almost 100 at the end of the third observing run. And if you look at the current situation, there's a public webpage where you can see all the significant detection candidates. For the fourth observing run, there are more than 200 potential detections. Of course, people are doing the data analysis to see if it's a real signal or not. But by the end of O4, we'll have maybe 300, 400 detections. So here's my favorite plot, which is kind of like a periodic table of black hole binary mergers. Has nothing to do with elements, but it looks a bit like that. So you have the 3 first detections and so on. And in every square, you have like 2 initial compact objects that merge to make one final object, and you can study their properties. And thanks to all those detections, you can do a lot of science. Whether you're interested in fundamental physics, in astrophysics, or in cosmology, you see that the list is quite long. And what I want to do is to give you a sort of overview of the kind of science we can do. I won't be exhaustive because it would take me way more than an hour, but just to give you a flavor of the kind of things. Maybe you're interested in testing gravity theory. Maybe you're interested in the way you form compact binaries. Maybe you're interested in the internal structure of neutron star. I don't know. Maybe you're interested in the expansion of the universe. Whatever your interest, gravitational wave science might help you. So if we start with astrophysics, in particular, you might question what are the channels to form compact binary systems. Before we detected this gravitational wave, we didn't know if black holes live in couple. We knew of binary neutron star systems with a distance large enough that we could not see them merge, but we could see them basically through electromagnetic observations, through so-called binary pulsar systems. And now we know that indeed they merge. We've seen some of those mergers, and also we've seen binary black hole systems, which you can't detect electromagnetically by definition of what a black hole is. So you can only see them or hear them thanks to gravitational waves. So if you look at the situation at the end of the third observing run, here's a sort of representation of the different kinds of systems that have been seen. On the y-axis, this is the mass of the object in solar masses from 1 to 200. And the idea is that you take, one black hole, say, of 8 solar masses and another one of, say, 35 solar masses, and it's going to make a bigger black hole. In blue, it's all binary black hole system that merge to make a bigger black hole. And in red, it's a neutron star. So here's a binary neutron star system with, say, 1.5 solar mass each to make a more or less 3 solar mass black hole. Okay? So one surprise. There are black holes whose mass is of the order of a few hundred solar masses. We didn't know that. We might almost call those intermediate mass black holes. We knew about stellar mass black holes through electromagnetic observations. We knew about supermassive black holes through other kinds of observations. Now we know there are also black holes in between. So that was kind of a first surprise. We also detected binary neutron star mergers, so that we knew the systems existed, but we had never seen them merge. So that was really nice. And also in conjunction with electromagnetic observation, as we'll see, you can get a lot of information. And we've seen mixed binaries, like a neutron star merging with a big black hole to make a slightly bigger black hole. So these are so-called neutron star black hole mergers. We were talking about Chandrasekhar with Giorgio 10 minutes ago, and Chandrasekhar showed that there is a maximum mass for a neutron star. You can't make a neutron star with a mass, say, larger than 3 solar masses. It's also difficult to make a black hole with a mass less than 5 solar masses. So people talked about a possible mass gap of compact object between 3 and 5 solar masses. And very recently, 2 years ago, in fact, there was a detection of a system with a neutron star with 1.4 solar masses, and some object whose mass is of the order of 3.6 solar masses, right in the mass gap. So this is most likely a black hole with a very small mass, and it's not obvious how to make such a small black hole. So, this detection, and depending on the masses you get, they're already kind of forcing people who study stellar evolution to go back to the blackboard and think about their theories about how you make compact objects.
Sorry.
Yep.
The Chandrasekhar argument was about the equation of state, right? It
Yeah.
wasn't the Schwarzschild radius, right?
Yeah.
Okay.
Yeah, no. It has to do with the
degeneracy pressure.
Yeah.
So much.
Of the strong interaction. Yeah.
Okay.
Yeah. Well, I think I'll skip this, but the main point of that plot was to say, once you get many detections, well, many sources, you may have a sort of stochastic gravitational wave background where you can't separate all of the sources, one from each other. And that stochastic background will hopefully be able to detect it also, not with current detectors, but with the next generation detectors. But that's a detail. Another very interesting thing is to study the origin and mechanism of so-called gamma ray bursts. So gamma ray bursts, we can detect them using gamma ray satellites in space. And there are short ones and long ones. And astrophysicists have wondered for a while, what are the mechanisms responsible for those gamma ray bursts? And we now have the answer for the so-called short gamma ray bursts, thanks to joint observation of a gravitational wave signal emitted by a binary neutron star system, and also a gamma ray burst observed by the Fermi satellite. And then observation of electromagnetic counterpart during the hours, days, months that follow that event. Basically, you had the LIGO and VIECO detector that saw this beautiful signal here, the so-called chirp. So the increase as a function of time of the frequency of the gravitational wave. And right here, when the two neutron stars are basically merging, right at that time, or less than a second later, you observe this short gamma ray burst. Then the question is, are those two related? They're related in time, but are they related in space? Is this coming from the same source? And indeed, if you look at the sky, the LIGO Virgo detectors can tell you that the source of the gravitational wave was inside this banana-shaped region in the sky. And there is one spot here inside where, and that coincides also with the Fermi, which doesn't have great capacity to localize in space, as you can see. But if you look electromagnetically, inside this common region, there is this galaxy NGC 4993, which is shown here with this little dot here that appeared right at that 10 hours after the event, which was not there before. So that's the electromagnetic counterpart hours after the merger of the two neutron stars and the associated gamma ray bursts. So that was extremely exciting for the entire astronomical community. And so in 2017, when this was observed, you had indeed really multi-mensageira astronomy, you could say that really started, right? Because you see the gravitational wave, the gamma ray, the X-ray, UV, optical, infrared, radio, everybody is looking at the same thing and deducing a lot of very interesting information, which I'm going to skip, but that was most importantly the confirmation that the progenitors of short gamma ray bursts are indeed the mergers of binary neutron stars. Now I'd like to talk about the tests you can do of gravity theory. So our best theory of gravity until today is general relativity. And clearly we cannot test general relativity in the so-called strong field regime in the solar system, because in the solar system, the typical deviation from Minkowski spacetime of the order at most of 1 part in a million at the surface of the sun. So we're living in a weak field domain of spacetime here. And to test gravity where the predictions are very, very different from Newtonian gravity, you need to be close to compact objects, or maybe eventually to study the expansion of the universe itself. And when you have two black holes or neutron stars that merge, this is typically the situation where you're in a very strong field regime. And so you have prediction of GR, which are clear-cut, that you can test with the gravitational wave observations. For instance, one thing you can do is check whether the initial masses and spin of the two, say, black holes that you have that end up orbiting and merging are consistent with the final mass and spin of the resulting black hole you get after the merger. So this is in principle something you can do by solving the Einstein equation, either analytically or using supercomputers doing numerical simulation, so-called numerical relativity. You start with your two bodies, given configuration, mass, and spin. They evolve and they merge, and then you have just one black hole, which will radiate still a burst of gravitational wave until it settles to an equilibrium state called a Kerr black hole, characterized only by its mass and spin. And there is a map between the initial situation and the final situation. And from the gravitational waveform, you can extract the initial parameters of the two black holes. And from the final part of the waveform, the so-called ringdown, which is like a superposition of damped sinusoids, like a ringing bell if you want, you can extract the final mass and spin of the final black hole. And you can check whether it's consistent. And this is what this plot is showing you. This is a relative difference between the final mass as measured from the ringdown and as predicted from the initial configuration. And same for the spin. So if GR is correct, the relative difference should be compatible with 0. This is a null test. And that's the case using, you see, half a dozen events here. All of the contours are compatible with 0, which means that this test of GR is indeed passed. With an accuracy which is not great because the signal-to-noise ratio is not huge, right? This is like maybe 50% or 30%. So it's not like accurate test of GR, but it's already a start. You can also constrain so-called post-Newtonian parameters. So what does that mean, post-Newtonian parameters? So you know that in the weak field limit, GR is going to reproduce Newtonian gravity. The Einstein equation is going to reproduce the Poisson equation. But you don't have to go straight to the Newtonian limit. You can keep, relativistic corrections. If you do that, you're in a regime called post-Newtonian theory, where you write the nonlinear GR equations and solutions of those equations as a background, which is the Newtonian physics, plus corrections called post-Newtonian correction that scale as powers of 1 over the speed of light. And so that will be especially accurate as an expansion if the typical velocity of your system is small compared to the speed of light, and if the typical strength of the gravitational field remains small enough, in a certain sense, to be made more precise. And in a regime where the separation between the two black holes is large enough compared to the typical size, and the orbital velocity is small compared to the speed of light, then you can solve the equation and write the equations of motion as Newtonian acceleration plus post-Newtonian corrections. And from that motion, you can also predict the shape of the waves. In those solutions, you have so-called post-Newtonian coefficients or parameters, and they have very precise values as functions of the parameters of the system, like the masses. So again, you can do null tests at different post-Newtonian orders. This is Newtonian order. First post-Newtonian order that would be of order v squared over c squared, second post-Newtonian order, third, and so on. Minus 1 pn you don't have in GR, but you have in scalar tensor theories when you have a scalar field that can also mediate a gravitational interaction in addition to the spin-2 fields of GR. And then you have dipolar radiation in that case, in scalar tensor theories. Just like, the moving of accelerated charges. And so you can constrain very well this dipolar radiation effect you see at the better than 1% level. And you can say there's none. At the 1.5 pn level, you have a very interesting effect called the gravitational wave tail. Basically, the gravitational wave emitted by the source is being backscattered on the background curvature of the source itself. So if you want to think about it in terms of light cone, the gravitational wave is not propagating only on the light cone, but also inside the past light cone because of that backscattering effect. And that is a generally strong field GR feature that you can test at the now 10% level. Also, you can test the final shape of the waveform after the two black holes have merged, and you have a deformed, excited black hole that's still going to radiate a bit of radiation as a sum of damped sinusoids. I already mentioned that. That's so-called ringdown. You see the shape of the waveform here will be just a sum over harmonics of some damped sinusoids with characteristic frequencies and decay timescales, which are functions of only the mass and spin of the black hole, which is perturbed and trying to reach its equilibrium state. If you wait a typical timescale tau here, that will go to 0, and then you will reach this Kerr black hole equilibrium state. So you can, again, do null tests here in terms of the frequency and damping time of the dominant mode, which is L equal 2, M equal 2, and the overtone N equals 0, the fundamental. And you see that, again, the null test is passed, again, with an accuracy which is not amazing, but better than nothing. And very recently, this paper came out, I think, a month ago. There was an event, which is almost like the first event that we saw 10 years ago. 230 solar mass black holes that merged. But now, of course, it's not the same source, but it has the same properties. And now we've seen it with detectors which are much more sensitive. And so it means we can get better signal-to-noise ratio. So that event, this binary neutral star that was seen, has a signal-to-noise ratio of 80. So you start being able to do more precise tests. And one thing you can test is the so-called area law theorem of Stephen Hawking, which states that when you have say, two black holes that are going to merge, the final area of the final equilibrium black hole has to be larger than the sum of the areas of the two initial black holes. Or if you take a single black hole, it doesn't have to be two that merge to make one. If you take a single black hole and you do anything to that black hole, you add matter in, you shake it, you do whatever you want, in the time evolution, the area can only increase. Okay? In fact, it's related also to the second law of thermodynamics. It's one of the connections between thermodynamics, gravity, and quantum mechanics. You can write laws of black hole mechanics, which are very analogous to the laws of thermodynamics, and it's a very good guide to quantize gravity. But let's stay classical. So you want to test this. So you want to test that the final area of the black hole that has reached its equilibrium state after merger is larger than the sum of the areas of the two initial black holes. So the fractional difference is shown here. So it means that the area Hawking theorem, you can't find a negative value. And also by energy conservation, well, I'm not going to detail, it can be much, it can be larger than 3. But here is the Bayesian, basically, reconstruction of the signal. So you see that indeed it's compatible clearly with the fact that the final area is larger than the initial area. So that's a test of this theorem, which is proved in the context of general relativity. So it's another test of GR, which is passed. You can exclude alternatives to general relativity. Many theoreticians love to devise, extensions or alternatives of GR, and some of the properties you can look for is how do gravitational waves propagate in those alternative theories. Typically, you have more degrees of freedom, like the scalar field I mentioned before in scalar tensor theories. You can also add vector degrees of freedom or several scalar fields or extra dimensions. I mean, many things. There's no limit to your imagination. And you can ask, how do gravitational waves propagate in those alternative theories? Well, we now know that the speed of propagation of gravitational waves is the same as the speed of propagation of electromagnetic waves to 1 part in 10 to the minus 15. Extremely constraining. So any theory that predicts, a speed of propagation of gravitational wave different from c, the speed of light, to more than that constraint is out. And so that's, all of those theories here are excluded by data. What data? Precisely the fact that you've seen a gravitational wave signal from a binary neutron star merger, and less than 1 second later, you've seen the gamma ray burst. So electromagnetic waves, and right after, gravitational wave, and right after, electromagnetic wave. 1 second after, but they've propagated on astronomical distances to get there. This is why you have such a sharp constraint. So anyone who's still working on this are not doing physics anymore. They are just having fun, mathematically, I guess. If you're interested in the strong interaction, QCD, maybe you could be interested in neutron stars, because inside neutron star, you're in a regime where the state of matter is typically characterized by the strong interaction. You need to understand strong interaction to understand the internal structure of neutron stars. And gravitational wave can be used to put constraints on nuclear physics. How so? Through the notion of tidal deformability. So the idea is quite simple. Just like you have the phenomena of tidal effect in the solar system, like you have the tides on the Earth because of the tidal field of the moon and the sun. If you have two neutron stars, the tidal field of one of the neutron star is going to raise a tide on the companion, and the size of that bulge, which will be raised by the tidal field of the companion, is going to be more or less big depending on how stiff is the equation of state of the neutron star is. So this is typically characterized by the so-called tidal deformability parameter lambda, which scales as the fifth power of the radius of the neutron star, and inversely to the fifth power of the mass. So that's what I'm showing here. So if you know about the notion of compactness parameter, the compactness parameter is the inverse. It's m over r. So the tidal deformability is 1 over the compactness parameter to the fifth. So the more compact the neutron star is, the larger the compactness, the smaller the tidal deformability, which you can see here. So this tidal deformability parameter, it is imprinted in the shape of the gravitational wave. You detect a gravitational wave, you put a constraint on the tidal deformability, and then you can put a constraint on the radius and also on the mass of the neutron star. So this is a mass-radius diagram of neutron stars. So the radius between, say, 8 and 14 kilometers. The canonical value is around 10 or so. And the canonical value of a mass is around 1.5. So you see that here you have like contours on constraints on mass and radius of neutron star in the binary neutron star merger, where you've been able to get this from constraining the tidal deformability. And then you have those gray curves, which correspond to different equations of state. For a given equation of state, you can say, well, for that mass, it should have that radius. Or for that radius, it should have that mass. Okay? These are those curves here. It's not necessarily a bijection, actually. And so you can see that, for instance, this equation of state is excluded by that data. So if you exclude that equation of state, you're learning about microphysics of the neutron star. Another example now in cosmology, if you do cosmography, one of the most interesting parameters, and you study the expansion history of the universe, is the Hubble constant, right? Of the order of 70 kilometers per second per megaparsec. That's one of the key parameters of the cosmological concordance model, lambda CDM. There are several ways to measure that Hubble parameter. You can use Planck data, for instance, of the cosmic microwave background, or you can use standard candles, type 1a supernovae, and there is a tension between the two measures. That's a tension between Planck here and Shoes. So Shoes is around 75 or so, maybe, and Planck around 68, and you have like 2 sigma error bars. So you see that they are not compatible within 2 sigma. So it would be nice to have a different way, independent way, to measure the Hubble constant. Well, gravitational waves can give you this. How so? Because if you get a binary neutron star merger, the amplitude of the wave, as we've said, is inversely proportional to the luminosity distance. So you have a direct access to the distance to the source thanks to the amplitude of the gravitational wave, on the one hand. And on the other hand, the gamma ray burst, or the electromagnetic observation afterwards, the afterglow, gives you the redshift. Because of the redshift of the electromagnetic wave, because of the cosmic expansion. And if you combine the two, the ratio of the two is basically giving you the Hubble parameter. And this is an unbiased measure of the distance, which is something very hard to do with electromagnetic waves in cosmology. So the typical result you get is the blue curve by doing this, combining eventually several signals. You see that the error is still much larger than the one you get from other means, but it's going to decrease as we get more and more detections. And interestingly, it seems to be so far compatible with the 2 other measures. So far, gravitational waves have not, settled the question, but we now have a new way, basically, to measure the Hubble constant without some of the issues that are present in other methods. I think I have, what, 10 or minutes left, or 15, something like that? Yeah, so I'm going to skip this and then just move on to the last section. I just wanted to mention that maybe you're also interested in the primordial universe, the physics right after the Big Bang. Maybe right after the Big Bang, there were some physical processes that generated some so-called primordial gravitational waves. Well, we'll be able to eventually detect those with future detectors and get information about the state of the universe very early on, eventually some phase transition or something like that. I mentioned a couple of times LISA, this proposal of a gravitational wave antenna in space. It was approved by the European Space Agency already back in 2017, with a launch plan less than 10 years from now. And LISA, who will basically orbit around the sun 20 degrees behind the Earth on the Earth orbit, has this triangular shape configuration. And there are lasers being sent back and forth. And as the gravitational wave goes through, it's changing the relative distance here between the arms. And this is how you can track the amplitude of the gravitational wave as a function of time by doing this interferometry in space. So you'll see many different kinds of sources. As a function of frequency, you have the characteristic amplitude here. These tracks correspond to binary supermassive black holes that are merging. You see that for two roughly 1 million solar mass supermassive black holes that merge in a galaxy, you expect to see signal-to-noise ratio of the order of 1,000 or so. So talk about precision gravitational wave physics and precision tests of gravity. You will also be able to observe so-called extreme mass ratio in spirals, which is when you have a stellar mass compact object, like a neutron star or a stellar mass black hole that we now know exists, orbiting one of those supermassive black holes. The orbit will be super complicated. It's not going to be like a simple circular equatorial orbit. There's going to be eccentricity, inclination, the motion. It's going to be very complicated. There will be harmonics in the gravitational wave generated. And basically, the small compact body is acting as like a probe of the strongly curved spacetime generated by the supermassive black hole in the center. And the gravitational wave is going to encode a lot of information about that central supermassive black hole. And so this way we'll be able to test also the nature of supermassive black hole and see if they really correspond to the black holes as predicted by general relativity. So that's what I'm talking about here. In fundamental physics, testing the black hole no-hair theorem. So that's something amazing in general relativity. If you have, basically a 2 or 3 parameter family of equilibrium black holes. If you forget about electric charge, which is not relevant astrophysically, any equilibrium black hole is characterized by 2 numbers, mass and spin. If you give me the mass and the spin of a black hole, I can tell you anything you want to know about the black hole. Everything is a function of the mass and spin of the black hole. For microscopic objects, this is unheard of, right? We are made of a huge number of particles, and if I give you my my height and my I don't know the size of my feet, you can't deduce what is my my age or whatever. Well, that's a bad example because it's always changing. But you see what I mean? Microscopic objects are very complicated, and black holes are the only microscopic objects which actually are extremely simple, as simple or even simpler than elementary particles. And we'll be able to test this, to test whether black holes have hair, what we mean by hair. Yes?
You were mentioning like speed for one of the characteristics of the black hole.
Yes.
Is it related to the angular momentum?
Oh, sorry, I meant spin angular momentum in the sense of the classical angular momentum, how fast it's rotating on itself, not in a quantum sense.
I see, but it's like the same thing.
It's a classical description. It's a classical description. So it's not related to the fact that the graviton would be a spin 2 particle. I just mean you have a microscopic object, and you need a general relativistic definition of angular momentum, not the classical Newtonian definition of angular momentum. But we do have this, and you can compute that for a given black hole, and that's well defined. And, yeah, that's what I mean by spin here. Sorry.
All right. Okay, thank you.
Yeah, that's a. Is it a word in English? Neologism, when you make up a word. Neologismo exists in Portuguese, right? I just made it up from geodesy. Geodesy is etymologically the science to measure the shape of the Earth. And so botromeladesy would be the science that allows you to measure the shape of a black hole. From botros and meladesia, I think, in Greek, which means black cavity. I checked in the dictionary, but I made it up. The idea is, if you put an artificial satellite in orbit around the Earth and you track its motion, you can constrain the multiple moments of the Earth this way. Because the orbital motion, the Newtonian orbital motion of the artificial satellite, encodes the gravitational potential. And the gravitational potential is sourced by a distribution of matter. So this way you can characterize the multiple moments of the Earth, which are exaggerated here on that figure. Similarly, the stellar mass compact object orbiting the supermassive black hole, I mentioned the orbit is going to be complicated, is acting as a probe of the space-time generated by the supermassive black hole. If the supermassive black hole is a Kerr black hole as described by GR, all of its multiple moments are only function of the mass and spin. The mass m, and a is the spin per unit mass. And so you see that all the multiple moments, they come in two families, mass type and current type, are related to these two parameters. So we'll be able to test this thanks to the gravitational wave generated by that system with LISA. In a regime where you have two black holes where the mass ratio is not extreme, but maybe it's two 30 solar mass black holes very close to merger, then there is going to be, in principle, a lot of tidal interaction and potentially deformation. So you may ask, well, one is not, a probe in the other one, which is not deformed. In that regime, really, the two are supposedly deforming each other. And you can try to characterize how those black holes are being deformed. There's a technical object for that. It's called love number, tidal love number. So with some colleagues, we computed the love numbers of spinning black holes. And this information should be encoded in the gravitational waveform. And this way, we can do so-called black hole tomography, thanks to gravitational wave observations. So that's for the future with LISA. Very exciting. So our prediction is as follows. So if you have an isolated black hole, but spinning, it will have some quadrupole moment proportional to the spin squared. That's the spin-induced quadrupole moment. Basically, it's oblate or prolate, I never remember. Oblate, I think. Just because, like the Earth, it's rotating on itself, so it's a bit fat at the equator and thin on the poles. Same for the Kerr black hole. But now if you take your spinning black hole and you put it in some external tidal environment because of some companion compact object, it's going to also develop a so-called tidally induced quadrupole moment, which is proportional to the quadrupolar tidal field here, and also to the spin. So interestingly, you find that the effect appears only if the black hole is spinning. If it's not spinning, it's not deforming. That was known before our work. What we did new here was in the spinning case. And I think I'm out of time, but I will just briefly mention some of the work I've been doing over the past 10 or even now 15 years has to do with modeling the gravitational waves I've talked about for an hour accurately. And we have different techniques to do that. We have post-Newtonian theory, when the separation is large between the two objects and the mass ratio can be arbitrary. So I mentioned that, the post-Newtonian corrections. In a complementary manner, if you have a large mass ratio, a small object and a big object, you can use black hole perturbation theory, where your space-time is going to be, a background of the Kerr black hole in the center, and then a perturbation, eventually a nonlinear perturbation due to the small object orbiting around. And that will allow you to describe the dynamics even in a strong field regime when the two bodies are merging. But in principle, if you have comparable masses very close to each other, both of those approximation methods are going to break down because you don't have a small parameter in the problem. So you can only solve this numerically using supercomputers so-called field, the so-called numerical relativity field. And using all those techniques, we can try to cover the parameter space and predict the shape of the gravitational wave emitted by all of those sources. So the problem is that the current waveforms we have are not good enough for the future detectors. In a paper that came out a few years ago, it was shown, in fact, that for the next generation detector, we will need analytical or semi-analytical models that have to be at least 3 orders of magnitudes more accurate than the current ones we have. And we also need to improve the numerical relativity waveform by 1 order of magnitude. So that means there's a lot of work for theorists to do to get even more accurate waveforms. Why? Because it would be really sad if you can detect a signal with a huge signal-to-noise ratio, and then because you're using templates which are not as accurate as the kind of error you have in your data, you have bias on the estimation of your parameters, and then it's going to propagate to all of the nice sense I discussed, right? So you need to not be dominated by some systematic bias due to a badly modeled source, basically. So hence the need for new waveforms, in particular in the case where the mass ratio is, maybe not extreme, but starts being far from comparable masses. For instance, this system, you have like a neutron star that merged with a 40 solar mass black hole or so. That's a mass ratio of 40 to 1. Here, post-Newtonian theory is not going to be very accurate for some regime I'm not going to enter, reasons I'm not going to enter into. And you might think that black hole perturbation theory is not going to work either, because the small parameter is 1 over 40, so it's not 1 over a million. But in fact, as I argued already 10 years ago, you can take the results from black hole perturbation theory and do some trick, which is based on restoring a discrete symmetry that you've broken from the start, to enlarge the domain of validity of perturbation theory all the way to masses which become comparable. So the idea is to simply replace this asymmetric mass ratio, which in its principle goes to 0, to the symmetric mass ratio, which is a natural parameter that comes in post-Newtonian calculation, where the two bodies are treated on equal footing. I'm doing nothing fancy. I'm just restoring a symmetry I know is there in the physics problem that was broken from the start in the perturbative scheme. And mathematically, it's just a substitution game. You just need to do it in a way which is consistent. And if you do that, indeed, you observe that the range of validity of the small mass ratio expansion or post-Newtonian, black hole perturbation theory enlarges significantly. And just to finish, here's the kind of result we get. In a recent paper, we compared the prediction from second-order black hole perturbation theory to the exact result from numerical relativity. So numerical relativity, you solve really the Einstein equation on a computer. That gives you the correct waveform in black here. But the problem is when the separation is too large, it's going to take a very large number of orbits before they merge. And so computationally, it's going to be very expensive. You can't do it. In principle, it gives you the solution. In practice, you don't have the computational power to do it. And so you need analytical or semi-analytical models. So my proposal is to use black hole perturbation theory in a regime where, in principle, it should not work. Here, the mass ratio is 10 to 1. And if you compare the dashed yellow curve to the black curve, they start dephasing only a few orbits before merger. So you can see here the dephasing between the two cases, numerical relativity and perturbation theory. It's only at the very end that you have a dephasing. The dephasing is here. So they remain in phase for quite a while. And the amplitude is very good. And we're comparing to the state-of-the-art post-Newtonian. Well, actually, very recently, that was improved from 3.5 pn to 4 pn. So if you want fourth-order perturbation theory in 1 over c squared, and you see that the dephasing in post-Newtonian theory, and the amplitude is much worse than what we're doing using black hole perturbation theory. And in the paper that came out, I think, last week, my colleagues showed that if you add spins to the big black hole and even to the small black hole, and you do things properly, you still can get this amazing agreement between the exact result you get from numerical relativity and this prediction, which in principle should only work when the mass ratio is extreme. But here you see mass ratio of 6 or 15. You're basically reproducing the correct result. So to conclude, well, just about that last part, for third-generation detector, we know that the mismatch error from these semi-analytical models has to be reduced by several orders of magnitude. So that means my colleagues and I have still a lot of work to do. Among the sources we are starting to observe already with LIGO and Virgo are intermediate mass ratio in spiral, with mass ratio maybe of the order of 30 or 40 or so. So not extreme mass ratio, not comparable masses. So far, we didn't have any modeling techniques that were reliable to predict the waveforms, to detect the system without any bias. I'm suggesting that black hole perturbation theory in the so-called post-adiabatic waveform can be used to do that. We have many now cases where we can show that there's a good agreement with the correct result as predicted by full numerical relativity, even in this range of mass ratios. And so in the future, what we need to do is, to not stay in this regime where the two bodies are spiraling, but also include the moment where the two black holes are going to plunge and merge to get this perturbed Kerr black hole I discussed. And we also need to generalize to generic orbits, because so far this was for a quasi-circular orbit, and we need to do it for eccentric orbit, inclined orbits, basically the generic situation. But I think this is going to be very, very promising for building, a sort of universal class of template waveforms that can cover the full spectrum of sources we're interested in. And I'll stop here, and thank you for your attention. Any questions?
I have a question.
Yeah.
Can you put this table with the excluded versus included theories based on the speed of light?
Sure.
Yeah. Because this is.
So that was here.
So once Lisa, I guess otherwise don't switch on. Once Lisa is up in the sky and collects data,
Yeah.
and you measure a log number, and you do measure tidal deformability of
Yep.
black holes, what will happen to this table potentially?
Well, one would need to, take every theory here, and for each theory, look at the black hole solution and compute the log numbers associated with those black holes, because it's not going to be the black holes of GR. And then you need.
Black holes with hair, right?
Yeah, it will be black.
Every extension
It will be.
gives you hair.
Yeah, exactly.
Yeah.
So there will be hair, and one of the properties will change will be the log numbers. So for instance, maybe in one of those theories, even without spins, the black hole has hair and deforms in a perturbing tidal field, while a non-spinning black hole in GR doesn't deform.
But you don't know which extension.
No, you need to do the calculation. Yeah. And then see if the effect, is large or not, and whether you have the sensitivity to put constraint on that.
Other questions?
It was all perfectly clear? I don't believe it.
But I'm curious about some topics. You mentioned this new experiment.
Lisa?
The future is new observatory.
In space? Yeah, Lisa, yeah.
Are there alternatives to the future of measurements in this area, such as because from my perspective, what we are improving is just enhancing the scale of the experiment, right?
Ah.
Like using the same I suppose, but bigger. No,
That's not the case. It's not the case. When you go to space, it's not just because you want to be more sensitive. In fact, LISA is less sensitive than ground-based detectors. The point is that in space, you get rid of some terrestrial sources of noise that you can't do without, such as seismic noise, such as a truck that comes near your detector, such as an airplane that triggers air waves that propagate all the way to the detectors. It's so sensitive, it detects relative variation in length of the order of 10 to the minus 20. So it's like on a kilometer scale detector, you're talking about a change of the order of 1,000 of the size of an atomic nucleus. It's crazy sensitive. It's like measuring the distance between the solar system and the closest star more than 4 light years away with an error comparable to the size of a hair, right? So when you go to space, you get rid of those kinds of sources of noise, and also you can indeed have much larger arms. And what that does, it's changing the frequency window over which you're sensitive. So that's one of the things I mentioned at the beginning. Maybe I was not clear, but LISA will be sensitive to gravitational wave generated at much lower frequency than LIGO and Virgo. And much lower frequency means much larger sources. So LIGO Virgo cannot see supermassive black holes. LISA will, but LISA cannot see, a 30 solar mass source. So it's not just you want, to go to space to make a bigger detector. You're also going to really change the frequency window of sensitivity, and therefore you completely change the kind of sources you're going to see. And therefore you're going to study different physics and astrophysics and cosmology.
Any questions? Okay, in this case, thank you very much.
Thank you.